It's this invisible force, right? It can heal, it can harm. It's literally all around us, but it's also one of the most misunderstood things in all of science. Yep, I'm talking about radiation. And today, we're going to pull back the curtain and really figure it out. So, we're going to go on a little journey from the absolutely tiny microscopic level all the way up to the macroscopic. Us. We're going to follow a single particle of radiation as it zips into the body and see the whole chain of events it kicks off. This is what leads to the long-term risks that actually shape global safety standards. All right, so our story starts in just a fraction of a second, way down at the molecular level. This is ground zero. It's the first point of contact, and it's where every single biological effect of radiation gets its start. Now, you probably think radiation damage is like a tiny microscopic bullet hitting your DNA directly. And yeah, that can happen. But, and this is kind of wild, that's not the main way it does its damage. See, since our bodies are about 60% water, the most likely target for a random particle isn't our precious DNA. It's a plain old water molecule. And this is what's called indirect action. So this is where it gets really interesting because it shows how one tiny event just snowballs. The radiation hits the water, seems harmless enough, right? But in that instant, it creates something called a free radical. The best way to think about a free radical is like a tiny, angry, unstable molecule. It's now desperately trying to become stable again, and it does that by ripping parts off of any other molecule it bumps into, and that includes your DNA. It's this secondary attack that causes most of the trouble. Of course, sometimes that tiny bullet does hit the target, and that's what we call direct action. A high-energy particle can just slam right into the delicate ladder of our DNA, snapping the strands. So right there you see the two main ways radiation starts the damage, either by creating chemical chaos around our important molecules or by landing a direct knockout punch right to our genetic code. Okay, so we've seen what one particle can do, but what happens when a whole bunch of cells get damaged all at once from a high dose of radiation? Well, that's when we zoom out from the molecular level to what scientists call deterministic effects. This quote is, 500 years old? But it perfectly sums up this whole idea. With these deterministic effects, the harm is totally predictable. It's basically guaranteed. Below a certain amount, the radiation isn't a poison at all. But the second you cross that line, damage is a sure thing. This graph shows it perfectly. Just look at curve A there. As the dose goes up from 0, nothing happens. See? The response is 0. But then, bam, you hit point A. That's the threshold. You cross that line, and a specific effect, like a skin burn or cataracts, is guaranteed to happen. And the higher the dose gets above that point, the worse the effect becomes. It's exactly like a sunburn. A little bit of sun, you're fine. But you stay out too long, you cross that threshold, and you will get burned. And what's really fascinating is that different parts of our body have totally different thresholds. So for example, it takes a dose of about 2 gray, we'll get to that unit in a minute, to cause cataracts in the eye. But for something like permanent sterilization, the threshold is higher. And this is precisely why radiation safety is so obsessed with the dose. Because when it comes to these guaranteed or deterministic effects, the dose really does determine the poison. Okay, but let's be real. Most of the radiation exposure we might encounter in our lives isn't a big, high dose. It's a low dose. And that brings us to a completely different kind of risk. This one isn't about certainty at all. It's all about chance. These are called stochastic effects. Let's just compare these two risks side by side. The high-dose effect, that's the one on the left, you see it has that safe zone at the beginning, right? The line stays at 0 for a while. But the low-dose, or stochastic effect on the right, well, that's a whole different story. That line starts climbing right from 0. What does that mean? It means there is no known safe threshold. Any exposure, no matter how small, is assumed to increase the chance of something happening. So here is the absolute crucial point. High-dose effects are like a sunburn. You cross a line, you get burned. And how bad the burn is depends on how long you are out. Simple. Low-dose effects, they're like buying lottery tickets. The more tickets you buy, meaning the higher your dose, the better your chance of winning. But the prize itself, in this case a cancer, it doesn't get more or less severe whether you bought 1 ticket or 1,000. It's just about the odds. And what exactly is the prize in this terrible lottery we're talking about? Well, the two main long-term probabilistic risks that basically form the foundation of all our radiation safety rules are cancer and genetic mutations that could potentially be passed down to future generations. So let's focus on the biggest one, cancer. How do we actually know that low-dose radiation increases this risk?
Well, the evidence comes from one of the most important and frankly most tragic long-term studies in all of medical history.
Take a look at this graph. It shows the rate of leukemia among the survivors of the atomic bombings in Japan. You can see this sharp, absolutely unmistakable spike in cases that peaked about 7 years after the bombings, and then it slowly started to decline. This was the first clear, large-scale piece of evidence that linked a single radiation exposure to a long-term increase in cancer risk. By following these survivors for decades, scientists were able to calculate the risk for different kinds of cancers. This table shows what's called the excess relative risk. It's basically how much your risk goes up for each unit of radiation dose you get. And you can see the added risk for leukemia is really high. And it's also interesting that the risk can be totally different for men and women for certain cancers, like lung cancer. And I really want to stress this point. This isn't some theoretical model. The data from what's called the lifespan study of these 86,000 plus survivors, this is the empirical backbone for the radiation protection limits that are used in medicine, in industry, and in nuclear power all across the globe right now today. Okay, this brings us to our final section. We've seen how radiation causes damage, and we know about the two different types of risks it poses. But how do we actually measure that risk? Because it's not as simple as just measuring energy. You're going to hear two units thrown around a lot, the gray and the sievert. The gray, that just measures the raw physical energy that gets absorbed by tissue. It basically answers the question, what happened? But the sievert, that's the one that really matters for safety. It measures the biological impact of that energy. It answers the much more important question, so what?
So why are they different? Well, because not all radiation is created equal. This table shows this idea of a quality factor, which is really just a biological damage multiplier. As you can see, 1 gray of energy from an X-ray has a multiplier of 1. But 1 gray of energy from an alpha particle, that's considered 20 times more biologically damaging. It's like the difference between getting hit by a bowling ball or a bullet. Even if they have the same energy, the impact is going to be very, very different.
And the good news is, the math is super simple. You just take the physical dose in grays, multiply it by that damage factor for whatever type of radiation you're dealing with, and boom, you get the biological risk in sieverts. This one simple step puts all the different types of radiation on a level playing field, which lets us accurately figure out the total risk.
All right, let's wrap this all up. If you forget everything else, just remember these 4 key things. 1. Radiation damage starts with direct hits on DNA or indirect hits through water molecules. 2. High doses cause guaranteed deterministic harm once you cross a threshold. 3. Low doses just increase the probabilistic or stochastic chance of getting something like cancer. And 4, the sievert is the key unit we care about for safety because it measures biological risk, not just physical energy. But, and this is a huge but, even with all this incredible science, there's still some big unknowns. This quote, which comes from the very committee that helps set a lot of these standards, admits that at super, super low doses, like the level of natural background radiation we all get every single day, we can't definitively say the risk isn't zero. The possibility that it's actually safe, well, it can't be ruled out. And that really leaves us with a central question in all of radiation protection, doesn't it? Science has given us these amazing tools to measure and manage the risks of radiation, but it also shows us the absolute limits of our knowledge, leaving us all to wonder, is any exposure, no matter how small, truly without risk?